Thus, this Kähler condition on the metric gives us a lot of relations for the Laplacian, I mean, these two Laplacians that we introduced last class. And using that, we will prove the Hodge decomposition. Okay, but well, in fact, today I'm not proving every detail, so I will skip some parts of the proof. I will leave them as exercises, and they are maybe they are not so easy, but but well, they're just very long computations, right? So okay, so the first thing I have to say is that something that I didn't explain very well the last class. So let X, consider XH a Hermitian manifold. Right? And take any point in X. Okay, so we know that in some coordinate system, the metric, so in some coordinates, in any coordinates, right? Around X, I mean, so we can think that X is the zero of this coordinate system C1 to Cn. We know that we can write this one form or the metric, right? We know that H is the sum ij equal to 1 up to n of hij dzi tensor with dcj bar, right? And something that I said yesterday is that we can always choose a coordinate system such that this matrix here is the identity, right? And that's not true. I mean, it's not true that we can choose always a coordinate system such that this matrix is always the identity. I mean, in the whole neighborhood around X. But what we can do is to choose a coordinate system such that so we can always choose a system such that the hij at 0 is the identity, right? At the point X, right? But we don't know what will happen in the neighborhood, right? I mean, we can, in fact, what we're doing is to take a coordinate system such that the tangent vectors, the canonical tangent vectors associated to the coordinates at the point X are orthonormal with respect to the metric H, but we cannot assure that it is orthonormal in a neighborhood, right? What we can do is to normalize it. I mean, to do this Gram-Smith normalization method or orthogonalization method. But when we do that, we will obtain a frame that it's orthonormal, but this frame is not necessarily integrable. Does not necessarily comes from a coordinate system, right? At each point. So in fact, this is the subtle point about taking a Hermitian matrix that is Kähler. Okay, so I will explain this a little bit more. And so what is the point? The point is that I use this fact, but we could have done it just taking the not considering that the vector field associated to these coordinates is orthonormal. We will just take this frame that is orthonormal, then we take the dual of this frame on the cotangent bundle, and using this dual cotangent, this dual frame, we can introduce the metric on the cotangent bundle and on all the wedge higher exterior powers of the cotangent bundle, and the thing is the same thing. I mean, we don't need it to be integrable, this orthonormal frame, right? So, so something that I did yesterday, I mean the last class, was that, for instance, I defined the Hodge star operator, assuming that I was in this coordinates such that the metric was the identity. I mean, I was like assuming that I was in the same case as in Cn with the canonical Hermitian matrix, right? When I define when I compute the Hodge star operator, I mean explicitly, right? And the thing is that that's not wrong. I mean, even though that I cannot choose these coordinates such that they are always the identity. If you think about the Hodge star operator, the Hodge star operator is an operator that it is defined. It's an operator that it's defined from a space of differential forms to a space of differential forms, right? But it is defined point-wisely. I mean, the image of the star operator in one differential form at some point will depend only on the value of the original differential form at that point. It's point-wisely the definition. You get a definition point by point, right? So at every point, you can choose a coordinate system such that at that point, the metric is the identity metric. And you can compute the things at that point, assuming that you're in the same case as Cn with the standard metric, right? And that's because the star operator is not involving more things than the value of the metric at that point, right? It's something that is defined point-wisely, okay? So in general, whenever you have some operators, so whenever you have some operator from a space of differential forms to between spaces of differential forms, that is defined point-wisely, right? So you can assume that you're in the case of the local case of Cn at 0 with the standard metric, the standard Hermitian metric on Cn, right? So you can assume that like Hij is equal to the identity in some coordinate system. Only if this operator is the value of I mean the way that the operator is defined depend only on the values of the metric at that point, right? So what do I mean by this? There are some operators that are not depending only on the value of the metric on that point. I mean, there are some operators that depend also on the values of the derivatives of the metric at the point. I mean, there are other operators. So which kind of operator we have already defined that satisfy this property? I mean, that are defined point-wisely. I mean, here, for example, we have all the operators that we have used so far. I mean, the star, we have the differential operators, the adjoints, we have the Laplacians. All these operators are defined point-wisely. But for instance, stars depend only on the value of Hij at the point, right? For example, here, the star. But this operator, for instance, this adjoint of the delta bar, this is an operator that depends also on the values of the derivatives of Hij, because you apply first you apply first, so this, remember that it's minus star partial bar star, right? So when you apply a star, it will appear a dependence on Hij, but when you derive it, it will appear a dependence on the first derivatives of Hij. So at the end, whenever you want to see some relation between operators that involve also the first derivatives or higher order derivatives of Hij, you cannot assume that you're in the case where Hij is the identity, right? Because at that point you have to make sure that there are some coordinates where Hij at the point is identity and also the derivatives of Hij at the points are 0. That's what you have to check in order to reduce yourself to this case. If you want to check, if you want to see that some relation between operators is valid in Cn, then it will be valid on a Hermitian or Kähler manifold, right? So for instance, the relation, this relation, right, double star equal to -1 to p plus q times the identity. This is valid because since it is valid on Cn. See, we verified on Cn, and since these operators only depend on the value of Hij at the point, we will have this relation also in any Hermitian manifold. You see? this is what I did, I mean, in the last class. I proved this in Cn, in fact. I took the coordinates and I did the computations on Cn, right? So this is the subtle thing that you have to keep in mind. And well, the Kähler condition on the metric will correspond exactly to the good condition in order to assure that there are some coordinates where we will also have that Hij is equal to the constant metric, the constant standard Hermitian metric on Cn, but also at the approximation, at the first approximation level, right? Also for the first derivatives, I mean, and that will imply that whenever we are trying, whenever we have a relation between operators that depend on Hij and the first derivatives of Hij, if this relation is true on Cn, it will be true on, in this case, on a Kähler manifold. Okay, that's the philosophy, right? So, so this is, I will prove this. This is a proposition. So let H be a Kähler manifold. Okay. Then for every x in X, there exists a coordinate system around X such that the metric, you can write it in this way. I mean, such that the corresponding metric, the corresponding matrix Hij given by the metric, it will be equal to the identity plus some functions depending on the variables C1 to Cn, but in order at least 2. Okay, so the approximation will the first order approximation of Hij will be equal to the identity also. I mean, it will be equal to the constant metric equal to the identity at the first order approximation. Okay, and the second order we don't know. I mean, if we want to verify some relation depending also on the second derivatives of Hij, we will not be able to assume that it is the identity. Right? Okay, so this is the proposition. The
Could you repeat the last part, please? Why do we do not verify some things when the related to second derivatives?
Because I mean, this is a function depending on z, right? This varies with respect to z, and the value at x is the value when z is equal to 0, right? So if we want to verify something between some relation between operators, that these operators are defined point-wisely, and at the point 0, for instance, in this coordinate system, they depend only on Hij at 0, Hij at 0 will be the identity, right? So we will be able to assume that it is just the identity, meaning the same case that we were in Cn, right? If it also depends on Hij prime at 0, I mean, some partial derivative of hij at 0. We will also be in the case, well, when we take the partial derivatives of this at 0, we will get 0. Right? So we can assume that in fact it is constant at first order. Right? But when we take the second derivative, here it might appear something like C1 squared. Right? And when you take the second derivative of hij with respect to C1 at 0, here will appear a 1. Right? Something different from 0. So you cannot assume that this metric is constant up to a second order approximation, because it's not. There are some coefficients that appear, and you have to consider them in your counts, your computations. You know, this is what I. Clear? Okay, so the proof of this proposition. Okay, so consider Z1 to Cn, a coordinate system. Coordinate system around X such that hij at 0 is the identity. Okay, we can always do that. Okay. So we use a Taylor approximation. So by a Taylor approximation, we know we can write hij, h as the following thing. So it is the sum from I equal 1 to n, dzi times dzi bar, plus the sum, let's say ij equal 1 up to n of some lij dzi times dcj bar, where this is linear, right? This is the first order approximation, and something of higher order. Right? Okay, so since this is linear, we know that we can write it as in coordinates, right? We can, so if taking zj equal to xj plus ij and zj bar equal to xj minus iyj, we know that we can write this lij as a lij whole, a holomorphic part, just depending on zj, on z1 up to cn. I mean linear, c-linear in these monomials, I mean, plus lij anti-whole, that it's depending on c1 bar up to cn bar, right? Linear polynomial with complex coefficients, right? Okay, so since this hij is Hermitian, we have that the lij whole bar is equal to the ljr ji anti-whole. Okay, this is the condition of being it Hermitian, right? I mean at the first order approximation, right? Okay, so and also we know that we can write the 1-1 form, omega. It will be I over 2, the sum from I equal 1 to n, dzi, which dzi bar, plus this sum ij equal 1 up to n, Lij whole, dzi, which dzi bar, plus ij equal 1 to n, Lij anti-whole, dzi, which dcj bar, plus something of higher order, right? And so let's give a name to this part. This part. So let's call this mu. Okay, so what do we know? We know that the metric is scalar, so that means that d omega is equal to 0, right? So in particular, we know that that delta bar omega is 0. No, delta omega is 0. Wait, what is the one that I want to compute? Yeah, delta. We know that delta omega is also 0, right? This is the condition. I mean, delta and delta bar are 0 at omega, right? And so what does that imply when we look at this formula for omega? Obviously, this will be 0 when we apply delta, I mean partial. Obviously, this will also be 0 because this is anti-holomorphic. And what I claim is that this will be 0. Okay? So I claim that this implies that partial of mu is equal to 0. Why? Since I know that the partial of mu at the point 0 is 0, right? Because I don't know what will happen with this higher order part, but since I know that it depends on z at order at least 2, when I derive it once, it will also be vanishing on 0, right? So I know that this is true for the point c1 up to cn equal to 0. But the thing is that mu is equal to this sum of ij equal 1 up to n of Lij whole dzi, which dcj bar. And this guy is a linear form in terms of z1 up to cn. So this is a sum, let's say, from k equal 1 up to n of some ck times zk, right? So when I derive it with respect to the holomorphic coordinates, what I will obtain is a constant form. So the derivative of mu, the partial mu, it's constant. It doesn't depend on the point that I am above, right? I am on. So this implies that delta mu at every z will be equal to delta mu at 0, that it's 0, right? For every z in the chart, right? So that's why this is delta close. Okay? Okay, so we know that this guy is delta close. In particular, mu bar is delta bar close, right? Okay, so now I will use some results from the complex geometry course and from the course of analysis on manifolds about the Rham cohomology and Dolbeault cohomology of Cn. Okay, so we know by Dolbeault lemma we know that this H, what will be this 1, 0 of Cn, we know that this is 0. Okay, this is Dolbeault lemma, and I think you should have seen it in the complex geometry course. Okay, this is like the Poincaré lemma, but for Dolbeault cohomology, right? I mean, okay, so by Dolbeault lemma, we know that there exists some B, right. So it is the 0, 1 that I want to compute. No, mu is holomorphic, so mu bar will be, it is a 1, 1 bar. Yeah, this one. We know that there exists some B 1, 0 form. Right? Such that the partial bar of B is equal to mu bar. Right? Okay, so if we, in particular, well, then the partial of mu bar is equal to mu. And if we writing B bar as a sum of, let's say, aj from j equal 1 up to n. So we know that B bar is a 1, 0, I mean a 0, 1 form, right? So it is a infinity function times dzj bar, right? Where this map is infinity. I mean this aj are infinity. Right? Is it clear? Yes? Is it clear? Okay. So if I write explicitly the form, what this equation is saying is that the Lij whole will be equal to the partial derivative of aj with respect to zi. Right? This is mu. Mu is equal to this, right? Ij equal 1 up to n of Lij whole dzi, which dzj bar. And if you derive B bar with respect to the holomorphic coordinates, you will get the partial derivatives of Ij with respect to Ci times dci wedge dcj bar. Right? So this is clear. Okay. Okay. So now so let's define the following differential form. So let eta, let's say, defined to be the sum eta j, let's say, for every j, the sum from I equal 1 up to n of the partial derivative of ij with respect to zi dci. Okay. So what happened when we compute this d of eta j? D of eta j, when we derive it with respect to the holomorphic coordinates, we will get like the delta of some, I mean, it's easy to see that this will be, let's say, ij, no, let's say ik dzij squared dck dci dck wedge dzi, right? And when we derive this with respect to the anti-holomorphic coordinates, it will be 0, because we know that it is equal to this Lij whole, that it's holomorphic, right? And this is 0 also because of this Schwarz thing, you know? This is 0. Right? So this is a closed form. Okay? This is a closed one form. So since by Poincaré lemma, we know that H1, the Rham of Cn, is 0, right? So there exists some, I don't know, chi. So that it will be again a C-infinity function, right? From Cn to C, such that d of z, well, let's say zj, I mean chi j, I don't know the name of this. Chi j is equal to eta j, right? And what does this mean? This means that the partial derivative of zj with respect to ck bar is 0 for every k, and also the partial derivative of Cj with respect to Zi is equal to eta Ji, I mean to the partial derivative of Ij with respect to Zi, that is equal to Lij whole. Right? And so now we're writing Lij whole as the derivative of something, but this something now it's not just infinity, it is holomorphic because it satisfies all these relations, right? So this implies that this guy is holomorphic. Cj is in O Cn. Right? And furthermore, we know that we can assume that Zj at 0 is 0. Right? Because we're taking partial derivatives of it. Right? So we can subtract its value at 0 and we will also have these relations. Right? So we are done here because with this we can take now the following coordinates. So considering so Zi prime defined as Zi plus Chi I.
Could you repeat why we can assume that C of G of 0 is equal to 0?
Because what I'm saying here is that there exists some Zj that is holomorphic, that at 0 is 0 and satisfies that its partial derivatives correspond to Lij whole. Right? So if it's not 0 at 0, we can subtract its value at 0. And it will also be holomorphic, will also satisfy these relations. So we can assume it. Okay? And so we take these new coordinates, and you will see that then you know that this sum I equal 1 up to n of the zi prime tensor with the ci prime bar, this thing will be equal to the sum of I equal 1 up to n dci tensor with dci bar plus the sum from ij equal 1 up to n of what? So you will have here the chi tensor with the ci bar plus the sum, I mean, no, this is zi, dz, this is I equal 1 up to n, dci, I equal 1 up to n of dci tensor with the chi bar plus something of higher order. Right? Because we're assuming that the chi's are 0 at 0. So when we take this tensor with the both of them, we will have something of higher order. Okay? And so what is this? The only thing that we have to do is to compute this. We know that this is the sum of its partial derivatives, right? J equal 1 up to n. So the partial derivative of dzi with respect to zj times dzj. Right? And so what will you get here? You will get here. Here you will get this will be the lji whole. Right? And when you do the same count here, you will have the, when you take the complex conjugate, j equal 1 up to n of l ji whole bar dc j bar, right? And this is the lij antiwhole. Right? So you will have that in these coordinates the metric up to order 2, up to an order 2 approximation, it will be exactly the identity. Right? This at this other side is where you have the original metric. Right? So the original metric in these coordinates is the identity. Right? The thing is that, well, here in this part we are adding something that is different, right? But it doesn't matter. Okay? Okay, so it's clear? So this is the important fact about having a Kähler metric. So now we will check a lot of different relations between operators, and we will check it just for Cn locally at 0, and we will deduce that they are also valid for Kähler manifolds if we're just if these relations only depend on Hij and Hij prime. Okay, so now I will introduce another operator that I haven't introduced before. So definition. So let xh be a Hermitian manifold of dimension n. Okay, with associated 1 form omega. Okay, then the Lefschetz operator is by definition the following operator. It's L from omega pq x infinity of x to omega p plus 1 q plus 1 x infinity of x, given by taking a form here and a form b, and you will take it to b wedge omega. Okay, this is the Lefschetz operator, and we denote by lambda its formal adjoint, right? And it will be equal to minus 1 to the p plus q the star L star, right? Since we have the following relation. So what's the relation? So L of some eta times phi in norm L2, it's equal to the integral over x of eta wedge omega wedge the star of c, and this is equal to the integral over x of eta wedge the star of c wedge omega, right? And now this is equal to minus 1 to the p plus q of the integral over x of eta wedge the double star of L of the star of C, right? Because we know that C is a p plus 1, q plus 1 form. The star will be n minus p minus 1, n minus q minus 1. When you apply L, it will be an n minus p, n minus q. And so the double star will be minus 1 to the n minus p plus n minus q, and this is the same as this. Okay. And and we're done, right? And this is equal to the integral over x of eta wedge the star lambda phi, right? Okay, so we will use a lot these operators, and all this we're doing it in order to get principally to the to relate these two Laplacians, right? The Laplacians, the Laplacian respect to d and the Laplacian respect to partial bar. And the point is that these operators depend on the derivatives that are order 2. Right, on the derivatives of the metric, and that's why we cannot do this computation just on Cn and verify it easily, right? That's why we will have to produce a lot of different relations that are like at order 1. And then using them we will be able to get the other relation. So this proposition, I will not prove it because it's quite long and not too enlightening. So let Xh be a Hermitian manifold of dimension n. Okay. Then we have the following relation. So we have that L, the commutator of L with lambda as operators, is equal to P plus Q minus N times the identity on the PQ forms. Okay, so check that L and lambda, I mean, they only depend on the values of Hij of the metric at the point, right? So in order to check that this is true, we just need to check it for Cn, right? If we check it for Cn, it will be true for any Hermitian manifold because L and lambda only depend on the values of the metric at the point, right? And furthermore, if let's say if H is scalar, then we also have the following two relations. Then we also have lambda, the commutator of lambda with partial bar is equal to minus I partial bar adjoint, and the commutator of lambda with partial is equal to I partial, this is partial adjoint, this is I partial bar adjoint. Okay, so the proof is proved for Cn. Okay, it's long. It's quite long, and I won't do it. It's an exercise. Okay, so what are the consequences of this proposition? So corollary. If Xh is a Kähler manifold, then the Laplacian with respect to D is equal to 2 times the Laplacian with respect to partial bar. And so this H, the harmonic PQ forms correspond to the harmonic PQ form with respect with D. This is by definition the intersection of the harmonic forms of the K forms with the PQ forms. The PQ forms that are harmonic with respect to the Laplacian, to the D Laplacian. Okay? So let's compute this proof. Maybe we'll do the proof here. So compute this. Laplacian d is equal to what? It's equal to partial plus partial bar, partial adjoint plus partial bar adjoint plus partial adjoint plus partial bar adjoint, partial plus partial bar. Right? It's d, the adjoint d. Okay, so let's compute this, and we will use these identities. So we will replace what? This guy. This is equal to I, the commutator of lambda with partial bar, and this is also I, the commutator of lambda with partial bar. Right? And so when we do this product, we will get the following thing. So here, this times this, it gives partial bar star, and here we have the other part. Right? So here we get one copy of the Laplacian. And what else we have? We have I times partial lambda partial bar minus I partial bar lambda, right? We also have I lambda partial bar minus I partial bar lambda partial plus some extra part that is obtained from here, right? It's the partial with the partial bar star plus the partial bar star partial. This part, okay. Okay. And now, so is there something that cancels here? Don't know. Okay, this will be equal to, this is the Laplacian partial bar. Here I have so here I will replace this, well, let's write these commutators first. So the commutators will be minus I. Yeah, I think I shouldn't have done that. Maybe I should just, I shouldn't expanded the commutators. I mean, this is just, so it's this with, is it with this with this. So it's I partial lambda partial bar, right? I don't like to do discounts. Okay, so this times this times this, and this other two times this, right? Okay, yeah, let's write the whole thing. Okay, so the whole thing is this. This partial E lambda delta bar minus E partial bar lambda, right? Plus so I will get E, yeah, it's right, lambda delta bar minus E delta bar lambda delta, yeah. Yeah, and here we will write this. This is the Laplacian plus minus I. So here we have delta, the commutator of lambda, no, of delta bar. Is the commutator of lambda with delta bar, right? This is this part minus this part and this other part, right? Here we have minus I partial bar, the commutator of lambda with delta, right? Yeah, here I am using that this is minus partial bar partial, right? And we have this other part, and this, and here I will replace the partial bar star with the commutator that is there, right? So this will be minus I partial, the commutator of lambda with partial, minus I, the commutator of lambda with partial. Okay. And if you compute this, this will be the Laplacian of delta bar plus, so what will you get? So what you will get is I'm not seeing how do I get this relation. Let me check it. Lambda with partial is I partial bar. Yeah. So here you replace this with this thing will be partial bar star, partial bar. This here you will get partial bar star, and when you compute this, it will give you 0, right? Because it will be partial lambda partial, and here you will get it with a minus, and when you apply partial 2 times, it will be 0 also, right? So you will get 2 times the Laplacian. Okay. Oof. If I barely could do this count would be impossible. Okay, another corollary, a corollary of the corollary is the following. So if xh is a compact Hermitian, well, a compact manifold, no, a compact Kähler manifold. Then every global holomorphic form omega is closed. Maybe you saw this in a Riemann surface course for Riemann surface, compact Riemann surface. Global holomorphic forms are closed. Okay, and why? The proof is very simple. So you know that if omega is holomorphic, right? We know that since omega is holomorphic, it is partial bar closed. Right? So in particular, it represents an element in the Dolbeault cohomology group. Right? Well, and furthermore, we know that it's obviously the partial bar star of omega is 0. Right? Because the partial bar, if we think of omega as a P0 form, the partial bar increases in 1 the anti-holomorphic part, and the partial bar adjoint decreases it in 1. So it will be like a P minus 1 form. That's 0. The space is 0. Okay? So in particular, it is harmonic. Right? So in particular, omega is harmonic. Right? Being harmonic, you know, is that the Laplacian of it is 0, and it's equivalent to have these two relations, right? This is what I explained it in the last class, in the previous class, right? And since we already know that this space is exactly the space of harmonic forms with respect to the D Laplacian, right? This implies that d omega and d star of omega is 0. Right? I mean, the Laplacian, the delta d of omega is 0. And this is equivalent to have this equal to 0 and d star of omega equal to 0. Right? Okay, so finally we are getting close to the Hodge decomposition. So a definition. Let X H be a compact Kähler manifold we define the PQ cohomology groups so the HPQ of X is by definition the following thing. So it is the kernel of the D of PQ forms X infinity of X D okay, so these are the closed PQ forms mod the exact PQ forms. Okay, so mod the image of D intersected with the PQ forms. Right, and this is obviously inside a subspace of the K, the Rham cohomology group. Right, it's the subspace of the Rham cohomology that is generated by closed PQ forms. These are the PQ groups. So now we have the Hodge decomposition theorem. XH be a compact Kähler manifold then we have the composition of the de Rham cohomology group as a direct sum of these PQ groups. Furthermore, we have that these PQ groups, they have a symmetry with respect to the conjugation, the complex conjugation. And furthermore, we know that we have that these PQ groups, they are nothing else than our classic Dolbeault cohomology groups, that they are isomorphic to these spaces of harmonic forms with respect to delta and with respect to D. Okay, so this is Hodge decomposition theorem. And we will prove it now. Okay, so you don't have questions so far? Okay, so proof. Okay, so it's not too difficult up to what we have done right now. So the first thing is to note that. So note that so we already know that we have this isomorphism, right? This natural map is an isomorphism, right? We already proved that in the previous class. And what we have to check is that this decomposition is true on this side, right? And it goes to the decomposition on this other side. Okay? So we claim that this H K D X is equal to the sum PQ of H PQ D of X. This means that whenever we take a harmonic K form, each PQ piece of the K form will be also harmonic, right? And that's easy because if we take any omega in here and we write it as a sum of PQ forms, we know that the Laplacian D of omega is 0. But it will be exactly 2 times the sum of P plus Q equal K of the Laplacian partial bar of omega PQ. Right? But the Laplacian partial bar of omega PQ is again a PQ form. So since we know that the PQ forms are independent when the PQ are different, this implies that this equal to 0 implies that every PQ form is harmonic with respect to the partial bar Laplacian. So then this guy is 0 for every PQ. And so since this is equal to 1/2 of the d Laplacian, this is also 0. Right? So we have this decomposition. Okay, so this is true. Right? And now the only thing that we have to see is that what's the image of these harmonic forms inside HK in the case of the Rham cohomology group. And we claim that it is all the HPQ group. So we claim that when we restrict this isomorphism to HPQ of D, there is again an isomorphism but with HPQ of X. Right? And obviously it's injective. The point is to see that it is surjective. Okay? And what's what I'm saying? I'm saying that whenever you take any element here, you have a harmonic representative of it, right? And how do you prove that? So let omega, a PQ form, such that d of omega is equal to 0. Right? So we already have this Hodge theorem of harmonic forms that I proved in the case of the partial bar Laplacian, but we know that it is also true for the case of the d Laplacian, right? All this thing of the green operator and all this decomposition of harmonic forms that I discussed the last class. So in particular, we know that we can write this omega as a sum. So we know that omega will be equal to the d Laplacian of the green operator associated to d of omega plus this projection to the harmonic forms with the d harmonic forms of omega. Right? We know that this is true by the previous class. Okay? And we know that this green operator commutes with d and d star. Right? And so this is equal to d times d star gd omega plus d star gd of d omega. And this is 0 plus a harmonic form. Right? Right? Yes? Yes, GD commutes with D. Right? I proved that the green operator commutes with partial bar and with partial bar star. Right? In this case, it's the same thing. Okay? Okay, and so yes, yeah, and the point is that maybe I shouldn't do it in this way. Yeah, maybe I shouldn't do it in this way. Well, no, I'm sorry. Well, we know that this is true. I will rewrite this. I mean, well, you will have to remember something about the last class. I mean, omega, when we define the green operator, we define it as, here it was the Laplacian of partial bar of something, right? Plus something harmonic, right? When we got our decomposition, this was a harmonic PQ form, right? And this was any PQ form, some PQ form, right? And what I prove is that you can find another PQ form such that this is Laplacian squared of B, right? And then I defined the green operator, the G of omega was defined as the Laplacian of B, right? Do you remember that? Okay, so let's take this decomposition first, I mean, with the partial bar. So we know that we also have a decomposition with respect to the D Laplacian. And this decomposition is unique. We also know that the green operator is unique, right? And we also know that this omega, this thing is equal to 1/4 Laplacian D squared of B, right? So that implies that the GD of omega is equal to 1/4 of the Laplacian D of B, right? Because this, I mean, this is D harmonic also, right? Okay, and so now we're done because so now this implies that omega is equal to Laplacian D of GD of omega plus phi, and this is equal to D of D star GD of omega plus D star of GD D omega that is 0 plus C, and this is harmonic PQ form, right? This implies that the class of omega is equal to the class of phi into the Rham cohomology. The class of C, and C is harmonic, right? So C comes from here. Do you see it? If I were just using the D theorem, the theorem corresponding to the D Laplacian, I wouldn't be able to prove that this was a PQ form. In principle, it was just a harmonic K form, right? That's why I should combine these two theorems. Okay. Okay, so from there we obtain the first part of the Hodge decomposition, right? We also obtain this part. This is equal to this and is isomorphic to this, right? This other isomorphism, we already have it We proved it the past class. And so the only thing that we have to check now is this symmetry, right? And again, in order to prove the symmetry, we just need to check the symmetry at the level of harmonic forms, right? And why is it true? So, and note that HPQ D of X bar is equal to HQP D of X. And the only thing that you have to check is that if you take a harmonic PQ form, you will get, and you take the conjugate, you will get a harmonic QP form. That's the only thing that you have to check, right? And that's easy because D of omega bar is the same thing as the bar of D omega. In consequence, the D star of omega bar is the bar of D star omega. And in consequence, the Laplacian of omega bar is the Laplacian of, so the bar of the Laplacian of omega. And that's all. Okay. And that's the proof. Okay, so what time is it? Okay, maybe I should stop here. I don't know if you have more questions. Okay, so next class I will prove a Hardt-Lefschetz theorem. It's not too hard from what we have right now. Okay, the Hardt-Lefschetz theorem is not that hard.